Hello and welcome back. Let's talk about volume integrals. Now this is quite a fundamental part of Calc 3. A lot of the time we're going to be talking about 3D space, so we need to know how to calculate the volume of certain objects. So volume integral is represented as the triple integral, since we're in 3 dimensions, over a volume E with respect to volume. This is just the same as adding up all the small segments of volume, the same way we did for, say, arc length. But yeah, let's just hop into an example, I guess. Our first example is just the volume of a cube. So I guess I'll draw the cube. Or not a cube, sorry, this is technically a rectangular prism. And it spans from x equals 1 to 3. So, this is reversed, sorry. X equals 1 to 3. We've got it spanning also from y equals 2 to 7. And we've also got it spanning from z equals 0 to 3. So this would be very easy to calculate. I decided we would just start with an easy example. Obviously we could just calculate it using the volume of a rectangular prism, but let's do it the fun way. So dV, I forgot to mention this, equals dx dy dz, which is pretty self-explanatory, I guess you could say. But it's not always going to equal this, but in cases like this, it will. So basically what we're going to do is we're just going to take, what does z go from? It goes from 0 to 3. What does y go from? 2 to 7. And what does x go to? 1 to 3. dx, because x is our first integral. dy, because y is our second integral. And dz, because z is our third integral. So first, we've just got let's evaluate our inner integral first. This is just 3 minus 1, which is 2. So let's just take the 2 on the outside. We know the integral of a small amount of some variable spanning from these two values is just the top value minus the bottom value. That's easy. Let's do it again. The integral of dy from 2 to 7 is just 5, so let's take our 5 out, multiply by 2. We've got 10 integrals from 0 to 3 of dz, and that's just going to equal, this integral is going to equal 3. We've got 30. And that makes sense because if we were to regularly calculate this, we would have 3 times 2 minus 7, or 7 minus 2 is 5, times 3 minus 1 is 2. This is also 30. If we had units on our axes, we would have units, but in this case we do not have units. I suppose we could say units cubed if we would like to. But just remember that our units are going to be cubed when we do things like this. Now let's talk about an example where dV does not equal just 3 simple terms. What could this possibly be? Let's calculate the volume of a sphere with a radius 5. There's a little diagram of it for you guys. So when we're using spherical coordinates like this, our integral is actually going to equal, still going to equal the triple integral over E dV, but with spherical coordinates, dv equals r squared sine phi dr d phi d theta. So there is a proof for this, but it's quite lengthy, and I don't really think it's that worthy of going over. It is a worthy proof because someone had to figure this out, but it's better to just memorize it in my opinion. So let's take this. Let's just move our integral over. This is the triple integral over e of this. Well, let's put some parameters in for e. First, r ranges from 0 to 5. Phi, as we remember, using our spherical coordinates, our phi comes off of the z-axis and can rotate all the way down 180 degrees, or pi radians. So it ranges from 0 to pi. And theta is the same as the unit circle. It ranges from 0 to 2 pi. So this is going to equal the integral from 0 to 2 pi, integral from 0 to pi of r cubed over 3 sine phi, evaluated from r equals 5 to r equals 0. Don't forget to keep our d phi d theta here because we still have to evaluate these two integrals. An easy way to keep track of this is just making sure you have the same amount of integrals as small amounts of some variable. So now we have the integral from 0 to 2 pi, integral from 0 to pi of, well, r cubed over 3 evaluated from 5 to 0 is a constant. We're going to take it out in front. It's going to be 125 over 3. Sine theta, or sine phi, d phi, d theta. The integral of sine is negative cos. So this is going to be very easy. Negative cos of pi is just negative 1, that's 1, plus 1, that's 2. So we've got, oh, I forgot my 125 over 3. Now we've just got 250 over 3, integral from 0 to 2 pi, d theta. So this is just going to take another 2 pi out. We've got 500 pi over 3. And if you'd like to do the calculation just for the volume of a sphere, you're going to get the same answer. And so obviously these weren't amazing examples, I'll admit, because we could have just used volume formulas, which would have been a lot easier. But we need to know this for other cases where, say, we have some crazy shape that we would never know the volume of using simple formulas. And this is also, well, some of these is how these formulas were derived. But thanks for watching. I hope to see you in the next video where we start to get into actually exciting stuff.